presentation is sponsored by the Innovative Teaching and Learning Committee of AMATIC. AMATIC is the American Mathematical Association of two-year colleges, and our core value is building expertise and exhibiting leadership in the teaching and learning of mathematics, enhancing personal growth, and improving teaching methods and effectiveness as a personally initiated lifelong responsibility. And for more information, you can visit us at amatic.org. And please note that the views expressed by the presenter are not necessarily the views of AMATIC, and any commercial products mentioned by presenters are not endorsed by AMATIC. And now we're going to switch to the presenter slides. However, I think that we're just going to have Martin share his screen today, so I'll put this up here so that Martin can share his screen with you. And if you want to welcome him in the chat room again, that would be great. And I'm going to turn it over to Martin right now.
Okay, well, I'm going to hope that this share works. Let's see how it goes. Is everyone seeing a window there? I can't see what's being shared yet. Anyhow, I'm pleased to be here, and are you seeing a screen? Somebody's typing something. You can hear me, that's good. So this webinar is going to be discussing trig functions, and if you see
Martin,
my,
could
yeah,
you click the down arrow next to the microphone button and adjust your volume up a little bit?
okay,
Next to the microphone button and adjust the microphone volume up a little bit because a few of us cannot hear you. I think that you muted it completely, so you'll have to go back and unmute it. But then under that is adjust microphone volume. Just turn it up a little bit if you could.
it's it's on. Are you hearing me now?
You're a little bit louder. If you could all let me know in the chat room if that's loud enough, that would be great.
How's that? Is that loud enough? I don't mean to blast people away.
Nope, that sounds better. Thank you, Martin.
Okay, is the screen up, the main screen up now? The title
It
screen?
is.
Okay, very good. So we're all set to go. And I just want to point out that on this main screen, you can see that there's a link there to the links that I put up in advance. And if you wanted to use those links um, during the presentation, you could, here's what they look like. And there's links there that attach to a previous webinar that I gave, and then there's some links here to some stuff. If you have GeoGebra, you can download the GeoGebra files. If you don't have GeoGebra, you can use these HTML files, and those will open up an HTML file. If your Java is good, you'll be able to do the GeoGebra through the HTML. There's some blank uh, paper here, sheets for mapping diagrams you can use as your own resources, and there's two worksheets that we'll look at maybe later. So, and there's also a Trig spreadsheet that you can download at your convenience. I'll be going through those as we pass through the webinar. So get back to the presentation here. Okay, and so I have a quick question or two for people. First of all, how many of you can raise your hands up or down? How many of you have are familiar with mapping diagrams? So quick hands up or down on that. Not seeing the tally here, but going to move on then and say that if you are familiar with them, I hope this will enhance your understanding. If you haven't, then maybe you will want to watch also the Using Mapping Diagrams to Understand Functions. That's another webinar that was done on AMATIC and is available on the AMATIC site. And I'm going to skip the next one because I'm not seeing any responses on my screen for what's happened with the question.
Martin, I think you just turned your mic off.
How's that? Thanks for letting me know. Okay, so um, stray moves of the mouse here. Um, I'm going to talk about first mapping diagram basics, then a little bit about triangle trigonometry and how mapping diagrams can fit in that, then the circle trigonometry where the mapping diagrams are a key connector to the circle trigonometry, then a little bit about the identities that you can visualize with the mapping diagrams, periodicity and the symmetry identities especially, and then on to solving equations and the related topic of inverse trigonometric functions, and finally, the real kick is understanding compositions of trigonometric functions and seeing how that works with mapping diagrams. So that's the outline using the mouse here. Okay. All right, we're okay now? Yeah. All right.
Yes.
So we're ready to go. So mapping diagrams basic, also known as mapping diagrams, also known as function diagrams, and there's been some recent use of the word dynagraphs to discuss these functions. So, am I still on? Okay. So before we get too far in, I want to show you where the bottom line is going to be. And so I want to show you how mapping diagrams would analyze this function, y is g of x. It's 3 sine of 2x plus pi over 3 plus 2. This is the kind of graph that students have to do in the sort of the end of the graphing function part of the Trig course, or a pre-calculus course, or elementary functions course. And so the way I want to think about this function is as a composition. So what do I mean by that? Well, you start off with a linear function, multiply x by 2, then add pi over 3. That's what I'll call u. That's the first step. Then the next step is find the sign of that result. So v, I'll call, is the sign of u, that result we had 2x plus pi over 3. Finally, you take the result that we just got, v, multiply it by 3, and then add 2 to it, so that y is actually equal to 3v plus 2. Now, this way of thinking about this function is not the way it's done in the textbooks. The textbooks recognize forms and talk about shifting things around on the original sign graph. I want to show you what that looks like when you think about this function as a composition with mapping diagrams. So here's what it will look like, and we'll be talking about this later in the in the um, webinar. But this is where we're heading to understand this mapping diagram. So on the left, we have the numbers that are put in. I've selected some of them, minus pi over 6 through 5 pi over 6. Now, the first function is the linear function 2x plus pi over 3. That's before we get to the trig, 2x plus pi over 3. So that's visualized by taking the number on the left-hand axis and multiplying it by 2 and adding pi over 3 to get to where the arrow points. So, for example, 5 pi over 6 gets to be 2 pi, and minus pi over 6 gets to be 0. Okay, so that's our 2 pi over 6 becomes minus pi over 3. You add pi over 3, you get 0. So these red arrows in the first section are showing us the mapping diagram for the linear function 2x plus pi over 3. The next section, the middle section, is the mapping diagram for the sine of u. We'll be talking about that at greater length, but you can see from 0 to 2 pi, the values are being sent over. 0 goes to 0, pi over 2 goes to 1, pi gets sent to 0, 3 pi over 2 gets sent to minus 1, and 2 pi gets sent back to 0. After that, we now apply the third function after the trig, 3v plus 2. So you take the values that came up, which we've only got minus 1, 0, and 1, and we multiply them by 3, add 2, and we get the output range here from minus 1 to 5. So the original function, y, takes the interval from minus pi over 6 to 5 pi over 6 to the interval minus 1 to, to 5, and it will be starting at 2, at minus pi over 6, it'll start at 2, it will go up to 5, then come back to 2, and go down to -1, and then come back up to 2. That will be the full cycle of our uh, trigonometric function in this example. And we'll come back to that, but I hope as we pass through the webinar, the ideas that are in this first mapping diagram will become more clear, and at the end you'll say, oh yeah, I understand that really well. So we're going to move on. I'm going to mention first of all, outside of as a reference, that I've been working on a resource for the future called Mapping Diagrams from Algebra Basics to Calculus and Differential Equations, and you can actually use this link, which is I think will be on the link page to get to the first section of that. Um, those materials. They're going to be free, open source materials about everything you ever wanted to know about mapping diagrams and maybe a little bit more. All right, so now we're going to begin more detailed introduction to mapping diagrams, a quick consideration of linear functions because they are the simplest and also some of the most important functions in all of mathematics. So we're going to look at this. If you want to download and try the worksheet that's available on the site, you can do that now. I'm going to move on and talk about linear functions. So first we're going to look at tables. Here's a typical table for linear functions. I usually do my tables vertically so that they'll match up with the diagrams. So on the left you see the column of the data that I want to compute, and I'm going to complete the table. And for the numbers 3, 2, 1, 0, -1, -2, -3, I start top down. And we may look at these questions. What's f of 0, and for which x is f of x greater than 0? Here's the data. And you can now look at the questions and answer them, I hope. f of 0 is 3. And for which x is f of x positive? Well, it looks like it's somewhere between -1 and -2 where it starts to get negative. And so we don't have a clear response to that, but it's certainly somewhere between -1 and -2. And we can come back to that later. So that's the tables. Graphing this, of course, if you familiar with graphs, what you do now from the table is you plot the ordered pairs. I have them here plotted. This was a graph that was made actually using Sage, but we'll just move on. And next thing you do might be is connect the points, and you've got what you might describe as the graph of the function from the data to the graph of the function by filling in the lines. Now, here's the way we deal with that with a mapping diagram. So we have the exact same data, but on the left of our mapping diagram, we put the source or the domain values, and I have the numbers that I've used here on this number line. So I'm thinking about the numbers being on a number line. And the values that come up, I'm also putting on a number line. Now, in this example, all the number lines are separated. All the arrows that go from the source input to the target value that shows up in the codomain, they all are independent. And if you want to think a little bit about how linear functions work, you can see that for every unit in the target, we have 2 units in the, every unit in the domain. Slow down, Martin. Every unit in the domain, we get 2 units in the target. So that's the effect of this number 2, and the value at 0 is 3. So the initial value, the value at 0 is 3, and the rate at which things is changing is 2. 2 units on the target for every 1 unit in the source. And that's an important thing, important concept in linear functions that the mapping diagrams makes quite clear, and you don't have to talk about slopes or other things like that. The diagram, the mapping diagrams take care of all that for that visualization for you. Okay, I've got a couple of other examples to show you here of the mapping diagrams. First, I want to show you an example in Excel. This is actually the trig functions, but I want to show you a little bit about how Excel will make this. So this is a trig function. Here's the sine, graph of the sine, and this is a mapping diagram for the sine going from 0 up until 2 pi. And you can see that the arrows are, they're not arrows, but they're going up and down. And I want to just show you quickly how this diagram is made because it's very easy, and Excel is one of the nicest features of Excel is that it will make mapping diagrams quite easily. So to start, I outline, and this is the data that I want to deal with, and I've highlighted it all. And then on my Excel, I'm going to go to the insert, because I want to insert a scatter plot. So I'm going to click on the scatter plot, and I'm going to do one with has pretty straight edge lines, and that's the graph of the scatter plot. But up here on the left, I see I can switch row and column, and here's what happens when you switch row and column. You get the mapping diagram. So that's the only thing you need to know to make the mapping diagrams with a spreadsheet. Most of the spreadsheets work the same way. You build a scatter plot, and then you just switch row and column, and you will get a mapping diagram. You can adjust it later as you please. So I'm going to go back now to the PowerPoint and show you now an example of this in, well, we'll get to the GeoGebra example a little bit later. So at this time, if you like, you can download the Trig worksheet because we're now ready to move on to trigonometry. So, of course, the first questions that students ask are, why are we studying trigonometry? And, of course, you start off with, well, they're important for solving right triangles. And then, why are right triangles important? Well, because they came into a lot of use in surveying and navigation and astronomy, and historically, that's the original stuff. And it wasn't just triangles on a plane, but it was spherical trigonometry that was important for navigation, especially for astronomy. But then after that, functions and modelings become important, and so we model things like sound and light with functions that are periodic, and periodic functions are best thought of as being related to the trig functions. And how do we do the trig? Well, we start with some right triangles, some key right triangles like a 30, 60, 90, or the isosceles right triangle, the 3, 4, 5 right triangle, or maybe the 5, 12, 13 triangle. Places where we use the Pythagorean theorem, and then we move to the unit circle, we make some tables, then we might even, historically, we might have used slide rules for dealing with the trigonometry. Eventually, we'd use our calculators, e-calculators, not the hand calculators or the whatever electronic calculator you have. Then we start talking about the graphs of these functions, and what we don't do is mapping diagrams. But that's what we're going to do today. So here's a look at the triangle trigonometry. And I want to look at this with a, so this is a GeoGebra file. This is Triangle Trig Site. This is one of the ones you can download. It's also available on the web through the HTML file that I gave you. So let's just stop a second here and see if anyone's crying out there. All right, everyone's sort of okay, I think. All right, so everyone's moving along here. And sorry for those. I've been so intent on the talk that I haven't watched the chat that much. I'm watching it now. Okay, so this is a right triangle. It's a 30-degree angle here, and you can see the sine of that is a half, and the cosine is, well, it's estimated as 0.77. And over here, I have a mapping diagram, and the blue arrow here is indicating the sine, and the purple arrow here is indicating the cosine, which is square root of 3 over 2 exactly. So that's for a 30-degree angle, and I'm going to just move the angle up, and I'm doing that by, I have this little button up here, and it's already been arranged so that when I move that up, I'm going to get, maybe it'll move up. Okay, I'll move it back up. I'm going to move it up to 60-degree angle, to 45-degree angle. There's our isosceles right triangle, and we see sine of 45 and the cosine of 45. We estimated them again on the decimals down here, and over in the mapping diagram, they're both square root of 2 over 2, and we see this. The arrows have joined together, indicating that for 45 degree, both the functions, the sine function and the cosine function, give the same result, square root of 2 over 2. Now I want to point out that this, the angles here are using a degree measure, but of course a change of scale would have that be in radian measure. They'd be the same points, only a change in the scale value, not the change in the point, indicating what was going on. All right, so we've got 45 degrees. We might as well move up to 60 degrees. That's about the limit of my picture here. And at 60 degrees, you see things have been flipped, and so the sine of 60 degrees is square root of 3 over 2 here, and the cosine is a half. And I'm doing the mapping diagram here with these very small values because I want the students to get used to the idea of assigning an input to an output, to think of these as functions. So input from the source, an angle measured in degree, output a real number between 0 and 1. And I can actually run a few more here. There's 15 degrees, and here's 0, showing us the extremes. And at the other extreme, if I get to 75 degrees, we're up close to 1 for the sine, getting closer to 0 for the cosine. And when we get to the 90 degrees, of course, there's no triangle anymore, but we have the extremes shown at 1 and 0 for the sine and the cosine. So that's our presentation of the trig with the, and here's a summary of that. Here's the table on the left that you would probably organize for your class, and here's the mapping diagram putting all that information together for the first values that you do. And these are only going from basically 0 to 90 degrees. Here's a little bit more complete table showing the other trig functions. We're mainly going to focus on sine, cosine, and tangents here, but you can see the other trig functions there as well in this right triangle table. And then, of course, you get to measure your degrees and your radians from 0 to 90, and you might get this table with a lot of data in it, obviously not found by the geometry that we've been doing in our classes, but maybe you set up a table and say, here's what the tables look like for the other degree measures, and the corresponding radian measures are shown here. Now, what we want to do is get these tables to look like mapping diagrams. And to do that, I'm going to move now to the circle trigonometry. And, of course, on the unit circle, we isolate the points on the unit circle with this chart, and we find the coordinates of these easy points related to the radian measure or the degree measure from the basic triangle that we looked at originally, the 30, 60, 90 in the isosceles right triangle. We get them on the unit circle. This is what you do in all your classes, and it's not unusual to get this. Here's where we're going to change our view, and we're going to start looking at how to find the mapping diagrams from this unit circle. So you might recall that the way you think about the unit circle is you start with a number t. So the t is on an axis already. That's measuring maybe in radians, because we're going to do radian measure here. So t is measuring the angle in radians. It's a length of the arc, and then you wrap around your circle t units on the circumference of the unit circle, and you find a point. And then, once you found your point, you read off the first and second coordinates. Well, the first coordinate is down here. That's the cosine of t. And the second coordinate is found on the vertical axis. That's the sine of t. All right? So, I want to now look at what that looks like in a mapping diagram. So we're going to go to another GeoGebra file. Now this GeoGebra file is also up there. It's sine, cosine, tan, inverse. It's the one that's the GeoGebra for all the beginning stuff. And you can also find it the HTML file that's linked to it as well. Now in this visualization, on the right-hand side, I have the number t representing the angle. And you see that it's also moving here on the left. That is not in control. This t is controlling everything. But you see it in its source, and you can see the angle being marked out here, the arc length being marked out as that point moves around. So that's our first thing. And actually, you can see right in the center here of the circle is a little noter of the size of the angle in radians, just to confirm that we are connected that way. Here's pi over 2. And here's pi. Now we go on the other side. It's going to do a little bit weird stuff here, but we'll just move it around, and we can see that how that looks for negative angles. All right, so now we've got our correspondence, and you can see the coordinates here. Now what I want to do is show you how the sine function looks in a mapping diagram and where it comes from on the unit circle. So up this in this corner, I'm going to click on Hide Show Sine if you have this going with you. And here's our function. So let's look over in the on the circle first on the left side here. So as I move the angle, the t here gives us the point, and then the point sends us right over to the point on the vertical axis, and that's the sine of t, and that's what's reported over here on the right on the target axis for our mapping diagram. So you go from t over to the circle to the vertical axis, and that's all consolidated in the mapping diagram on the right. So as I move this, we see here's the sine of 0 is 0. Here's the sine of pi over 2 is 1. And here's the sine of pi back to 0. And we can go to negative. Sine of negative pi over 2 is minus 1. And the sine of minus pi is back to 0. So if you start at minus pi and you move from there, you see it go down, then come back up, then go up, and then come back down. And as you notice, I also have on the left-hand side, I have the graph of the function. And if you want to see that, what it looks like with the coordinates, there's the coordinates for the graph of the function. And so watch the point. The point is moving on the graph of the function as well as the t changes. So that's the connection between the mapping diagram and the graph. I'm going to take out the coordinates now and go back just to our sine. And we're ready to move on to our next trig function, which is the cosine. All right, so I'm going to take out the sine for a second and put in our cosine. All right, now this one, the cosine, remember, is the first coordinate. So we start at t, we go around the angle till we get to the point on that the quote wrapping function gives us, and then we read off the first coordinate. Now, in this diagram, what I've suggested is, you know what? It would be nice if it was on the same axis. So I've just flipped the value on the x-coordinate on the x-axis, on the horizontal axis, up to the vertical axis. And you'll see that that's moving along. So as I change the t, we get out to 1. And we come back down here. And it's just flipping that down onto the vertical axis from the horizontal axis in a rather nice symmetric move. But that allows us to keep track of what's going on from the vertical domain axis to our target axis. It's the same y-axis again that we see over on the right-hand side as the cosine function mapping diagram. Again, we start at 0 and we're at 1. So when t is 0, we're at 1. And as we move it up, it gets smaller and smaller, comes down to 0, and keeps getting smaller, down to negative 1 at pi. If we kept going, it would come back up. And I'm going to stop there and start down at minus pi. And so here we are at minus pi. And the value is going up to 0, then going back up all the way to 1 as we finish, as we get back to our starting points. So the neat thing about that is that it's keeping track of everything that you're doing, everything that's going on the right-hand thing without having to think about the circle, but we have the source of this mapping diagram coming from the unit circle and actually getting the mapping diagram from the unit circle information directly. So we don't have to do any translation into coordinate systems, which is what we see in the graph here. This is the graph of the cosine, and if I put the axes back in, you can see that as the familiar graph of the cosine showing up, and we're moving along on that graph as we move through the angles from minus pi to pi. Okay, so that's the sine and the cosine. I'll take my axes off again. And now I want to move on to the tangent, which is a really interesting one, and a lot of people don't use this feature of the tangent when they study the tangent on the map on the unit circle. what they frequently do is they just say, well, take the ratio of the sine over the cosine. But in fact, if you draw the line that's tangent to the circle at the point 1, 0, so you draw this tangent line right here, you draw that tangent line, then you can see on that tangent line how the tangent function is constructed. So here's my angle, and I'll put it at about pi over 4. Okay, so, well, it should be about pi over 4. Well, let's see if I can get it to be. It is about pi over 4. So what's happening here? Well, when we go out, we're going out 1 unit to the right and going up amount, so that if you think about the tangent as the opposite over the adjacent, the opposite is the measurement, the adjacent is just 1, so it's just the opposite, that it's this length here on the tangent line that's measuring the tangent. And so you can take that number and just shoot it right across to our y-axis, if you like, and we have it on the same y-axis that we've been measuring everything else. And so here's our tangent at 0 is 0, going up, getting to 1 at pi over 4, and at pi over 2, it disappears. Why is that? Well, because if you try and draw the line through the point at the top of the circle there, that's never going to meet the tangent line. So there'll be no tangent to measure there. So that becomes 0. Now when you go across pi over 2, you draw the line from the point on the unit circle through the center, and the tangent meets down on the negative side, and so we see the negative values of the sine of the tangent, the negative values of the tangent coming up as our response for these obtuse angles between pi over 2 and pi. When we get to pi again, we're back to 0, and we can again start getting more positives as we go along. So we see the vertical asymptote showing up, the fact that it's very, very large, showing up at pi over 2, coming back down, and if we go to the negatives, we see the same kind of thing happening at minus pi over 2. And then we get positive values coming up and getting closer to 0 as we get back to minus pi. So that's the tangent. It's measured on the tangent line, and we're just shifting it after we find it onto the y-axis so we can see it on our mapping diagram on the right here. Moving along. And again, I have the graph of the tangent showing up here, and you can see your familiar graph of the tangent line and the values showing up as ordered pairs on that tangent line as we move through the mapping diagram now. So you see the correspondence between the mapping diagram information and the point on the graph, which has the input and output showed as a single point rather than input and output as 2 points with an arrow connecting them, showing the relationship. Okay, so that's our quick trip through the mapping diagrams for the sine, the cosine, and the tangent. Now, I'm going to come back to this in a second because I want to make a note about how the mapping diagrams help you visualize periodicity. So let's go back to the mapping diagram here. I'm going to go with the sine for a second and put the sine up there. And now what I'm going to do is I'm going to take the sine, I'm going to bring it down here to minus pi. And what I want you to watch is the mapping diagram, not the circle right now. I'm just going to see what happens with the values. They're going up and down, oscillating a lot. Now, if we go back to the circle and look at the left-hand side of the circle, you can understand what the periodicity is all about. Here it comes, coming back down to our original range. The periodicity of the sine, which repeats every 2 pi, is because the point on the unit circle that we've got here, that point is moving around the unit circle, and the circumference of that circle is 2 pi, so it gets back to the original values after it's gone around 2 pi. If I start at minus pi and work from there, we see it move around, and when I get to pi, it's come back to the original point, and it's now going to recycle again. So every 2 pi, the values will repeat, and that's the reason for the periodicity of the sine evidenced in the unit circle and also visualized quite nicely, I think, in the mapping diagram in the fact that the values on the target are just going up and down, like a yo-yo or a spring oscillating up and down. So that's the oscillation for the sine, and I'm going to go back to the cosine and just quickly illustrate the same thing with the cosine. Again, oscillating again, the same 2 pi reason, and we'll go back. And now we'll look at the tangent oscillation, which is a little different because now we know that the tangent is going to start repeating not every 2 pi, but starting here at minus pi over 2, as I move forward, the values come up, they get very large, and then they jump back down and repeat in the next pi. So the period of the tangent function is pi. One can see that from the mapping diagram and the visualization of the tangent function on the unit circle. Alrighty, let's go back. There's our tangent, and again we can note here's the picture that visualizes our tangent on the unit circle and the periodicity. Well, we've already talked about periodicity. I want to talk a little bit about how even and odd are represented on mapping diagrams first, and then see how they work on the trig functions themselves. Well, I'm running a little bit late on time here, so let me just point out that the equation for the even functions is that f of a should be the same as f of minus a. On the mapping diagram, that means that if you go up a or down a from the number 0, you'll get the same value on the target. So the symmetry here is in the fact that things that are symmetrically located with respect to 0 on the input give you the same value on the output. Odd functions have the function at the opposite being the opposite of the value. So in odd functions, you actually, in the mapping diagram, you actually see symmetry on both the source and the target. They will be opposite. In this one, they both are, the values are, the value of f of a is bigger than the value of f of minus a, but they could be flipped as well. Here's the correspondence between the mapping diagram and the graph. So the usual mapping diagram visualization, not so usual, new to you, compares to this graphical visualization. So the value at a and minus a are the same. That means they're going to be symmetrically located with respect to the y-axis on the graph. A nice feature for the graph, a nice feature for the mapping diagram as well. Here's the odd functions, and this again is the usual visualization of an odd function for a graph, and here's the way it looks on the mapping diagram. So there's a nice symmetry for the odd function on the mapping diagram, which is a little bit easier to understand than the one on the graph, but they both are consistent. The odd and even symmetries of the sine, cosine, and tangent can all be seen from the way that the mapping diagram transfers into the circle. So the sine of t and the sine of the opposite of t are going to give us opposite things there. So that's going to be odd. The cosine of t and the cosine of the opposite of t give us the same value, so that's going to be even. And the tangent gives us, for the angle and its opposite, gives us opposite values, so the tangent is an odd function. So those are all easily visualized and understood by using the unit circle and the mapping diagram concept. Solving equations. Okay, so what does it mean to solve a simple trig equation? It means if the equation is solve the trig function of x equals z, you find the z on the target axis, then you trace back on any and all of the arrows that will hit that z, and you notice this connects to the periodic behavior of the trig functions and the issue of the number of solutions in the interval. So here we are on our mapping diagram again. Let's go back to sine, and we'll get back to, oh, just take sine here, okay. So here's a sine, And let's say we want to know when is the sine equal to 1? Well, it's equal to 1 only at this one spot. So that's at pi over 2, but then because of the periodicity, it's also true at um, minus 3 pi over 2, and we can keep going every 2 pi to see that. But for other values, it happens more than once. So for example, if we want to know when is it 0, well, it's 0 here at 0, but we know it's also 0 at pi. And if we want to talk about when is it this value, well, this is a little bit trickier, but you take a value in there, it will appear at this spot here, and it also appears symmetrically over here. So there's two spots that will do it, and then you have every 2 pi. So I'm going to see if I can find that spot over here, right about there. That's where it hits. So there are two places symmetrically located with respect to pi over 2, and um, that allows you to see that there's two sort of fundamental solutions to the equation, and then you use periodicity to get the infinite number of them, 2 pi away from each of these two sort of fundamental solutions to the equation. Same thing works for cosine. Tangent has similar issues about solving equations with infinite number of them, and then you just have to look at the difference by pi because of the fact that the periodicity of the tangent is pi. Now, this connects directly to the idea of the inverse sines. So I'm going to look at the arc sine. So that's the angle whose sine is a given number. And let's see if I can find that number that I want to use here. I think it's right here. So this is the number, and that's a y value. And that you never get any solutions with when is the sine equal to 1.54. You're never going to get that. But when I bring it down into the circle, I do get some values. And you can see now that what you do is you take the value of the y, you draw across to the circle, and then you read off the angle that goes with that, the acute angle that goes with it. So that's the arc sine. And if you move to the negative, you see it on the other side as well until you get to minus 1 where it disappears. So that's how the arc sine is connected to the circle, and we see the inverse function taking us from the values from minus 1 to 1 back to the angles between 0 and between minus pi over 2 and pi over 2. That's our arc sine. Similar thing for the arc cosine. We'll do that rather quickly here. Same kind of thing. Arc cosine, the angle is cosine is 0. The angle is cosine is 1 is 0. And then we move down, we get to 0. But here's the interesting thing. When we move past into the negatives, we get bigger angles because we're reading off of the x-axis here. And so we read an angle between 0 and pi for the arc cosine. Again, something that's easy to understand from the unit circle. You can do it from the graphs as well. It's just a little bit better connection to the mapping diagrams. And we see the mapping diagram taking us back to where we started. Arctangent's similar. The nice thing about the arctangent is the arctangent works for every number. So we get angles whose tangent are any number that we like, and that angle is going to be between minus pi over 2 and pi over 2. So we get that nice feature. Again, reversing the arrow, starting off with the value on the y, reading that off of the tangent line, and then reading back to the center and reading off the angle that went with that. So that's the mapping diagram for this. Now, the nice feature about this is that we can now think about, well, what if we take the sine of an angle and then find so here's the sine of an angle. What if we want to know the angle whose tangent is the sine of that angle? So we take our arctangent and just put it right there. So you find the sine of the angle, then find the arctangent. So what we have here is that the arctangent of the sine of 1.89 is 0.76, and that would be radian measure. So the mapping diagrams allow you to see that composition of functions, of the trig functions, the inverse trig functions, visually, and then you can, if you like, see that composition. Just follow the arrows in the order they're given, and then if you like, you can justify them with looking at the triangles that are related to these in acute triangles if you have an acute triangle. But if it's not an acute triangle, if I take the sine, let's do the arc sine here. So if I have, students frequently get confused. If I take the sine of an angle and then I take the arc sine of that, I get back what I started. But if I take the sine of a bigger angle and then take the arc sine, I don't get the same thing back because the arc sine only gives us answers between minus pi over 2 and pi over 2. So if I take an angle that's bigger than that, I'm not going to get the original angle. And this visualization with the mapping diagrams makes that very clear. Okay, so this is the pictures that go with that for solving the trig equations and the inverse functions as well. I'm going to skip ahead now. We'll get back to this maybe, but I want to do compositions. We're running out of time. I think we're almost out of time. John, how am I doing for time? John, you
We
there?
have about 5 10 minutes, 5 to 10 minutes left. So
Okay.
if you want
Yeah.
to see if anyone has questions now,
Yeah.
that might be good as well.
Let me just do a quickie on the compositions because that's what I said I'd end with. So compositions with trig functions. The basic idea is you do your sine. So here's our sine mapping diagram, and then you just add 3. That's our linear function. So the composition is visualized this way. First do the sine, then do add 3. Here's what the graph looks like for that. Here's the original sine, and here's what the add 3 does. It's a shift up 3. But now we understand that the shift up 3 is really happening. It's just a linear thing added to the number before. Here's what happens if you do 3 sine of x. So first you do the sine of x again here, and then you multiply by 3. So multiplying by 3 is going to change the 1 to a 3, the minus 1 to a minus 3, and all the numbers in between are just going to be expanded out. So we understand that the amplitude of that result function is going to be 3. The period is going to be the same as the original function, and so we can see that on the graph as well. The period is still 2 pi. The amplitude is 3. Now what happens if you do something before that, like let's do sine of 2x, and you want to solve an equation? Well, you can do that. I want to move to the graph of that. Mapping diagrams, what happens when you add a number or multiply, and I'm going to move to the last of the diagrams here. So I've got some mapping diagrams here, and here's my x, and this is just the basic sine function, and not doing anything before or after. And if I change it, so I'm going to change the b, which is going on before. I'm going to make that 2, and you can see over here the wave has been contracted, and it's traveling twice as fast. And I want to show you why that works from the mapping diagram point of view. So here's what happened. The g is multiplying the values of x by 2. So when you got to pi over 2, the input to the sine function was now pi. So we've already got through half of the sine wave. We go up to pi, and we've gotten through the whole sine wave. So let's take it back, and you see, so you start at 0. It's the multiplication by 2. That's the composition before you do the sine in the mapping diagram that's got us through the wave in half the time, and it's moving faster as it moves. The amplitude is still 1, but the period now is just pi because we've gone twice as fast. You can see how the other numbers affect it here. D is the shift. I'll just shift it up a little bit by 1. That's changing the values on the target by 1. I can make the A, that's the amplitude of the function, be a little bit bigger as well. Let's make that 3. And now when you look at this, you can understand what's going on. We're going faster because of the composition before we hit the sine. We're going faster, but the wave is getting bigger because of what's happening after we do the sine, and the period is just pi. The amplitude is 3, and there's a phase shift as well. I don't have the phase shift, but you can study that as well. That just comes by, again, changing what's happening before. So there's a shift so that to get that to be 0 at the start, you have to move down someplace else to get the 0 to start. And there's your start of this phase shift right there. Okay. Well, I think that takes care of the composition a little bit. I'm sorry we don't have more time, but I think that does explain that example that we started with. You're doing 2x plus pi over 3 here, you're doing the sine wave here, and you're finishing off with the linear function 3z plus 2 at the end. Okay, that's the graph. That's the end. I have some references here. There's the links that I gave you before. There's the diagram book. There's some other materials. These will all be put up on the web. Some other materials, Sensible Calculus, and some work by Henri Peixoto on mapping diagrams as well. Very nice stuff. And this work by Goldenberg and Lewis and O'Keefe, who have used the term dynograph to talk about it. That's the end, really. Okay, I'm ready for questions. I hope I have time.
Yes, if you have
John,
any
you there?
questions, just type them in the chat. And I'm going to stop sharing your screen so I can put up the survey link, if that's okay, Martin.
Okay, yeah.
Okay, let's.
So questions. I'm still looking for questions. You're welcome. Alex, Zalo, and Katie, any questions? Seeing a lot of thanks, and I'm
Well,
very thankful for your thanks.
well, let me just thank all of you again for participating in today's AMATIC webinar. And if you'd like to support future AMATIC webinars, please consider becoming a member of AMATIC if you're not already at bit.ly/join-amatic. And please remember to like AMATIC on Facebook at facebook.com/AMATIC. And recording of past AMATIC webinars can be found at bit.ly/amatic-webinars. And it typically takes us 1 to 2 weeks to produce and upload webinars to this archive. And if you could please take 2 minutes to evaluate the webinar content in the presenter at bit.ly/amatic20, that would be great. And if you need email confirmation of your participation in this webinar, please fill in the optional section at the end of the evaluation. And if you have any questions, again, please put them in the chat room for Martin. And I think that I speak for everyone, it looks like, as well, that the presentation was great, and thank you again, Martin.
Well, thank you all. I can't say you were a great audience because all I can say is thank you for all your thanks. But I enjoyed it, and I will be putting up these slides and the links to the stuff you can download, either the HTML GeoGebra or the straight GeoGebra files on those links. So you'll be able to carry on with this further, and I hope you'll come to look at the materials I'm putting up on mapping diagrams as well when that gets finished. I'm working on the Trig section this summer, so I hope that the Trig section and the calculus stuff will be done by the end of this year 2014.
Okay, well, thank you again, Martin, and I'm going to end the